Once again, thank you very much for inviting me for this great opportunity for us to talk anything about innovative concrete. My name is Harn Wei Kua. I'm the lead of the Smart Materials Lab in the Department of Building. And at the same time, I'm also the trust lead for construction 3D printing in the School of Design and Environment. So for the past few years, my focus has been on studying a special kind of concrete and mortar, and that is biochar concrete, biochar mortar. So this afternoon, my talk will be basically on giving you a historical account and description of what has actually gone on in this field for the past few years. And in the process of doing that, I would like to highlight a few milestones along the way so that we can actually trace how this field has progressed through the years. And of course, I would like to end this afternoon's talk by highlighting a few challenges ahead that hopefully some of you may be interested to join me in tackling in the near future. And of course, what are the opportunities open to us? Of course, on a topic like biochar mortar, it only makes sense for me to start by talking about what biochar is. So biochar as a topic of research and development is actually nothing new. It is a solid byproduct from thermal processes such as gasification and pyrolysis of biomass, mostly I would say wood, and even food waste, which I'll talk about later as well, under a condition in which very limited supply of oxygen is provided in the heating process at relatively low temperatures, and usually it is about or lower than 700 degrees Celsius. So from appearance, we might not be able to tell the clear difference between charcoal and biochar. So right here, you can see my mouse, my pointer, all right? So this is the feedstock, and after making, this is how it looks like. So what is the difference between biochar and the more conventional char or charcoal is that in the making of biochar, typically our conditions of production are very well controlled. Conditions such as the temperature, the residence time of the feedstock at this temperature, the heating rate, the cooling rate, not to mention, of course, the very careful choice of feedstock. So before I go into the history, or rather my personal history of how I got into this field of biochar mortar and biochar concrete, I'd like to share with you a story. So this is a real story which happened back in April 2015. So slightly more than 5 years ago. So I was on a short study trip to Cambridge University, visiting one of my old friends from grad school. And at that time, he was leading a bamboo construction material lab in Cambridge. And at that time, of course, I was also interested to look at the use of bamboo for construction. Although my approach is quite different from his, as you can see here, my approach is about how I can extract bamboo fibers and make use of these fibers in a highly alkaline concrete environment. Whereas the group in Cambridge, they are more into the application of bamboo in bulk. So the second question that I had when I was visiting Cambridge is, how do we, in general, improve the bonding of fibers to concrete matrix or cementitious matrix? So it was one fine day when I was just walking around the compound in Cambridge University, and then I came upon an idea. So the picture that I'm going to show you now is the picture that started it all, at least for me. Started me on the path of biochar mortar research, and this is it. Okay, it's a little bit, it's authentic. This is exactly what I've drawn after I've gotten this idea. Okay, so I apologize if it is not very clear, but in the middle, you can see that right here, that is the bamboo fiber. So the whole idea is about how I can encase the fiber of bamboo, okay, in a casing under the protection of a polymer, any kind of polymer. At that time, I have polyester in mind. But in order to improve the bonding between the surface of the fiber and the polymer matrix, somehow I got an idea of making biochar particles out of bamboo. So over here, you can see this. And of course, at that time, I have the idea of making use of the biochar particle to absorb as much carbon dioxide as possible. And this is represented here. So as you can see, it is written here on the top left-hand corner to be shared with Suradip. At that time, Suradip was my PhD student. So he has now graduated. So he's now Dr. Suradip Gupta. And as you can see later on, he and I combined, co-authored quite a few papers for the past 5 years on different aspects of biochar concrete. And of course, it's very interesting for me to share with you that I drew this picture just before I got onto the bus to travel from Cambridge to the airport. So it shows that you can do science and you can do research anytime, anywhere. So back in Singapore, almost immediately, I asked Suradip to come to the lab and we talk about this. And I even personally such coating can be done. But the problem that we face is that back then, we don't have bamboo fiber in the lab. So we changed our idea to make use of polypropylene and later on PVA fiber, but still retaining the concept of putting a coat of cement paste containing biochar particles in that as a way to protect the fiber and as a way of connecting the fiber in a better way to the cementitious matrix. And it is during this course of research when we try to conduct experiment and at the same time trying to gather more information about the literature and on this project and on this awesome concept of biochar concrete that we begin to get into the literature a little bit deeper. And from there, to me at least, it became very clear that there are pioneers in this particular field of biochar concrete. So with this page, with this slide, I would like to pay my respect, pay my tribute to 4 groups whom I feel are really the pioneers in this field. The first is definitely the group from South Korea, led by Choi. This group, in my opinion, might have been the very first group who have written and published an article on the use of biochar in mortar. But of course, at that time, they used a rather high dosage of 5% by weights of biochar made from hardwood, resulting in an improvement in a compressive strength of between 10 to 12%. Of course, anytime you talk about biochar concrete, you cannot not mention this guy, Hans Peter, a friend of mine, Hans Peter Schmidt, in the website of the IBI, the International Biochar Initiative, wrote a few pages on several of the on-site demonstration projects using biochar containing wall plaster. In fact, it is so interesting that 3 years later, in 2017, I actually made a trip to the mountains in Sion, Switzerland, just to visit him and his family. Spent 2 days, 1 night in the Ithaca Institute, and to really get in that whole sites of how biochar containing wall plaster, cementitious plaster can be applied on a large scale. 2015, and I believe this should be quite familiar with Professor Farrell, and of course, Dr. Restuccia. Ahmad and Tel, in my opinion, published an article which really opens the door to this field. And guess what? They studied biochar made from bamboo, produced at 850 degrees Celsius at a pretty high heating rate of 60 degrees Celsius per minute for 1 hour. And what actually capture our attention is that the compressive strength of the cement paste was increased by 40 to 50%, and of course toughness by 103%, and the flexural strength by 66%. And 1 year after that, and I especially highlighted this because it concerns the both of them. All right, Dr. Restucia and Professor Farrell found out that there's no need for you to push up the weight percent of presence of biochar. With as little as 1% by weight, you are able to substantially increase the fracture energy of cement-based composites. So, in my opinion, these 4 papers and perhaps a few more actually define the opening milestone of the field. And to me, the period between 2012 and 2016 actually underlines the realization of how biochar, with its filler effect, can actually help to improve the different mechanical properties of mortar and concrete. So with that idea in mind, it became relatively easier for us to follow up with more work starting from 2017. So from this point on, what I'm going to do is that, as the name of or the title of my presentation suggests, I'm going to define, at least in my opinion, the different milestones starting from 2012 in this relatively young field of biochar mortar. Okay, and of course, the literature is quite substantial, and given 1 hour, it's impossible for me to go through everything. So what I'll do is just to highlight a few of my own work and the work of our collaborators, as well as our friends in this area, that kind of define these different milestones in this young field. Starting in 2017, we begin to see effort of how we try to define the role played by what I call pore size effect, and how pore size effect can work hand in hand with the filler effect afforded by biochar particles to improve other properties, physical properties of biochar concrete. And one of them is the property of water permeability. And around that time, I would say that given that biochar research is not a new field, there's already been a lot of work done on how to make use of biochar as well as activated carbon or carbon sequestration. So there are a couple of work in this period in which these 3 effects actually are studied at the same time. And this is what I call the complex interplay of these 3 factors. At this point, I would like to highlight about the issue with water permeability. When I started this working on biochar mortar, one of the first things other than mechanical property is water permeability. And why is that the case? For those of you who are familiar with Singapore, you will know that we have a rather hot, humid, and extremely rainy weather condition. It's interesting to see how this guy needs to carry an umbrella to go into the house because of water leakage problem in many of the buildings in Singapore. And of course, nowadays it becomes better, but a site like this, as shown in the bottom left picture, is quite common. I still remember when I was young, my mom used to need to go up, reach up to the ceiling and patch everything up with this. So that's super mom. She's able to do everything and just trying to see how she can patch up in order to mend any water leakage. In fact, there was a survey that shows that out of 10 building-related complaints, 6 of which involve water leakage. And as we all know, as a material scientists and civil engineers, right? Water leakage is never ever just a cosmetic problem. It can be more than that. So as is shown over here, it can cause corrosion, spalling, and it's definitely more than just staining on the surface of the concrete. So it is with this motivation that when we started off doing this this research, other than looking at mechanical properties enhancement, we try to see how effects such as the filler effect, effects such as the pore size effect of biochar can help to improve the water tightness of mortar and concrete. So meanwhile, back in my concrete lab in NUS, this is what we did, investigating the filler effect on the strength and water absorptivity as fiber coating, meaning that we make use of biochar coating on PP fiber and see how it affects the properties of concrete, both strength and water absorption. And that's not all. We try to play around with saturating of biochar and try to see how sequestered carbon on the surface of the polymer, which is now contained in the coating that contains the biochar, can affect the properties and including the water absorption. So on the top right-hand corner, you can see a very simple setup, which is now becoming quite famous within my group, and we keep calling it the water tank, the fish tank experiment. So when you come to my team and when you mention about fish tank, everybody knows that this is the setup. So what we try to do is basically putting biochar here of different grades made at different temperatures and so on, and then just keep pumping carbon dioxide into the restricted space for a certain period of time, until the time when there's no more changes in the readings here. Then we take it out, and we are sure that the biochar is already almost fully saturated with CO2. So what did we do, and what are the results? So over here, okay, this is 4 clusters of bars that shows you how the coefficient of water absorptivity varies with the different control and the different specimen. There are 2 controls. The first one, control 1, is basically mortar containing PP fibers in the same proportion as the rest, where control 2 is just our plain mortar mixture without any PP fibers. There are 2 bars, the darker one and the lighter one. The darker one represents initial absorptivity, which is basically water absorption into the mortar specimen due to capillary action, due to the micropores, either in the mortar or in the biochar. And something is quite clear here, and that is these 2 clusters, which represent mortar containing biochar coating around the PP fibers, are on the whole much lower than the control. And I think that's good news, because it means that the filler effect of the biochar is able to plug any air gaps on the surface of the fiber. But what is even more interesting is that those fiber that contains saturated biochar seems to be higher compared to those with fresh biochar. Fresh biochar are biochar that is not saturated with CO2. So it seems that the porosity over here, when the biochar is fully saturated with CO2, is higher. Why is that the case? Well, when we compare this with the 28-day as well as the 7-day compressive strength test results, we see the same message, and that is that when you have fiber that contains saturated biochar, the 28-day strength is even lower than the 2 controls. So that seems to be in contradiction with our conventional knowledge of how carbonation can end up strengthening mortar and strengthening concrete. We went on to do our investigation, but this time we did something different. So instead of having fibers and having biochar as the coating for this fiber, we took out and we exclude the fiber altogether. So our main objective here is to study and compare mechanical strength and water absorptivity of mortar containing biochar only, without fiber. And of course, the biochar can be either saturated with CO2 or not containing any CO2. And this is what we found. So over here, we are talking about the depth of water penetration, which is a slightly different experiment compared to what water absorption or water absorptivity. Because in this case, we are basically subjecting our specimens to an external temperature of between 5 to 6 bars. But the results is similar, that whenever you have biochar that is saturated, it seems that the porosity is higher than when the biochar is unsaturated. And again, we see the same trend in the measurement and the comparison of compressive strength at 7 days as well as 28 days. So what we found is this: although carbonation, and that is the conversion of calcium hydroxide or even calcium silicate hydrate into calcium carbonate, may to some extent strengthen the mortar. But when you have excessive calcite formation, especially on specific concentrated area in either on the surface of the biochar or on the surface of the fiber, these are just going to be regions of weakness, of structural weakness that can cause debonding from matrix. And although this may not show up as increase in porosity or water accessible porosity, but under external loading, this weakness will show up. And there are also other studies in the literature that support this view as well. But of course, the good news is that if you have to look at the contribution of unsaturated biochar in the mixture as well as coating, you find that it can help to reduce water penetration, in this case by about 57%, and increase compressive strength, as in this case by about 16%. So these results are already published in CCC, as shown over here, and which happens to be one of the highly cited articles for this particular journal. But just because we show that carbonation has given us, relatively speaking, negative results, does not mean that we should not entertain that idea of using biochar mortar as a way of sequestering carbon or CO2. So at this point, I would like to talk about somebody else's work. So it's a recent work by Prime et al. And of course, the full list of authors is given here. They did something quite differently, and I would like to very briefly go through this. Top left-hand corner, you see that there's this M20. Well, that means that they basically make use of fly ash to replace away 20% of the cement in the mortar mix. And of course, M50 over here means that 50% of the cement has been replaced away by fly ash. But of course, they did things a little bit differently. They did not dose the biochar particles with CO2 directly. So they make use of CO2 as a curing or during the curing process. And these three sets of graphs on the left is what they measure after 3 days of continuous CO2 dosage. So the result is quite different from ours. So in a nutshell, what they have shown is that when you have formation of, or when you have carbonation, which is accelerated by the CO2 curing of the curing mortar specimen, the strength is higher, which is shown in all the orange bars. But on this side, all the green bars over here, which is indicated by my pointer, these are all taken at 28 days. I mean, they couldn't possibly keep dosing all the specimens continuously with CO2 over 28 days. And that's why they only measured the strength for, or they only measure and compare the strength of the mortar specimen when it is not carbonated. That means CO2 curing was not administered. So what have they found? CO2 curing is yet another way of carbon sequestration. This is a more conventional way, but what I find interesting is that they apply this to mixture that contains biochar. And what they found, which is what I've already highlighted, is that enhanced carbonation increases the early strength. And what is more interesting is that if you are to look at all these three sets of green bars, the highest strength is basically achieved at about 4% or 6%, which is typically higher than what we have done or higher than what we have managed to achieve in our own studies. And the reason for this is that they have fly ash in the mixture. And it is the pozzolanic and filler effect, the combined effect of the fly ash, that more than compensated for any increase in porosity when you increase the percentage of presence of biochar in the mortar mixture. So this is really interesting. And well, along the same line, as I've highlighted just now, we will want to know how the pore size effect and the filler effect can also work hand in hand in order to affect the different properties of mortar. So it is with this objective in mind that we explore the influence of particle size, as in the size of the biochar particle, as well as the size of the biochar pores on rheology, the hydration kinetic strength, water permeability of cementitious mortar. What we did differently in this case is that we produced two different types of biochar. Okay. The first kind is called NBC, which is manually grounded or manually ground with a D50 of only 10 microns. But on the other hand, we took one step further and to produce what we call GBC, which is basically biochar ball milled to a very, very fine form with a D50 of less than 1 micron. So what do we do? In order for us to find out exactly how important the contribution of pore size will be on the properties of biochar mortar, we intentionally cure, or we intentionally introduce two curing conditions to this experiment: moist curing and air curing. So I'm going to briefly go through this, and so that you know the implication of the results. So these two graphs shows the water absorptivity with time, how it evolves with time. So the higher the curve, basically it means that the higher the water accessible porosity will be. So the top green arrow here indicate this curve, which is for the control mortar. But at the bottom over here, you find that many of the graphs actually collapse onto one another. And these curves correspond to both NBC and GBC. So what does it mean? It means that when you have moist curing, that means you have the mortar curing in water all the time, it does not make any difference whether you have big particles or small particles, and whether you have big pores or small pores. For that matter, when we grind down any of the NBC to GBC, we basically break up the macropores into meso and micropores. All right, so we can almost think that NBC has more macropores, whereas GBC primarily meso and micropores. However, when we subject all the specimen to air curing, the condition is less forgiving. Right? The top curve corresponds to the control, whereas the bottom curve now it coincides with GBC. So it means that when you have air curing, where there's a lot of water evaporation that happen within the few hours, having small pores actually help, in this case, in reducing the overall porosity of the specimen. And how about the comparison of compressive strength? So this is quite a busy slide or busy table. So I'm going to make it easy for you, and you can then focus on this particular block first. So in this block, basically, what we have are the numbers and values for GBCs. 0.25 means that we have added only about 0.25% by weights of the GBC into the mixture, and so on. And of course, all those below are NBCs. And likewise, we have two kinds of curing conditions, moist curing and air curing. So what we found is that under moist curing, when you have the same percentage of dosage, in this case is GBC at 2%, this is the value, NBC at 2%, this is the value, there's very little difference, which means that it doesn't really matter which kind of biochar you use. However, the same message holds in air curing, all right, and there is a greater difference in between whether you are using GBC or NBC. And of course, in this case with GBC, when you have smaller pores, you end up having distinctively or significantly higher strength. So the key points, key lessons we learn is that it is not just about the size of the biochar filler anymore. Given the right condition, you need to use the right kind of biochar with the right pore size distribution. And of course, over here, we find that the coarser or the rougher, the bigger biochar particles will have stronger effect on the rheology. And do we have an actual picture to support our conclusion? Okay, yes, there are plenty, and they are shown in the paper that we have published. These are pictures from taken from what I call the wonderful world of biochar and biochar pores. And what we can see is how much or to what extent that the additional surface area afforded by the different pores can act as surface of nucleation for hydration products to form. And even to the extent of taking a peek and taking a look at the calcium silicate gel, and even one of my personal favorite picture here, the presence of ettringite. And the dead giveaway of ettringite is, of course, the needle-like appearance over here. So this is what had gone on starting 2017, and there is more and more papers along the line of studying a combination of different properties and different effects and different function of biochar mortar. Next, getting closer to where we are now, starting in 2018, I begin to find that there's a deepening of a general understanding of other contribution of biochar in mortar and concrete. So it's not just confined to mechanical properties and water permeability. I mean, these are important, but we are also looking at some of the other properties such as shrinkage and even what we call the reservoir effect. So in this study, our key research question is this: how will biochar affect the mortar and concrete shrinkage, drying shrinkage, as well as autogenous shrinkage? So the objective is to understand the impact of increased dosage on the mechanical behavior, the shrinkage, as well as, of course, the water permeability properties of biochar mortar. So on the top bottom left-hand corner, this shows you how the density and therefore the porosity of the mortar changes with the different dosage of biochar. So it is very clear that the more you add, the higher will be the porosity, and therefore the lower the density. And in this case, we produce two kinds of biochar at 300 and 500 degrees Celsius. And as indicated by these two red arrows over here, the more you add, the higher the porosity. But what is interesting is that if you are to compare the mortar porosity of plain concrete, or rather plain mortar, with that when 1% biochar is added, you find that there is a drop in porosity, and that can be attributed to the physical results of the filler effect. Then you have a lot of these tiny particles in the midst, and therefore it increases or it decreases the porosity. However, the more you add, you find that we'll reach a tipping point in which the emptiness, the pores on the biochar particles itself will take over, and therefore driving up the mortar porosity, as is shown over here. In this paper, what we have done differently is this. We try to get a rough idea of how, by addition of biochar, you can help to change the drying shrinkage of the mortar specimen. So in this graph, the y-axis represents the percentage change of drying shrinkage. So when you have positive, it means that there's an increase in the drying shrinkage. Negative, that means there's a reduction in the drying shrinkage. And what we found is that when you have biochar added at about 1%, you tend to be able to retain the moisture better, and therefore reducing the percentage of drying shrinkage. So that, I think, opens the door to a lot more opportunity in the future, as we all know that drying shrinkage, especially for a climate like Singapore, is a real issue. How about a comparison of compressive strength? Well, if you are to look at after 7 days, the difference between if I'm going to have 1% and 2% addition of a biochar in the mortar mixture for both 300 and 500 biochar, and the trend after 28 days, the message is clear. That the addition of only 1 or 2% of biochar made at 300 and 500 can help to increase both the early strength and the 28-day strength of concrete. So the message is also the same over here when it comes to water permeability. But of course, what is worth stressing here is that when you add too much, and what I meant by too much is as much as 5%, you will end up driving up the porosity and therefore the water absorption. So this is to show you what we have seen under the microscope, okay, of the condition of the mortar when we have too much of the biochar made at 500 degrees Celsius. When it comes to the reservoir effect, remember that just now I mentioned that this is the time when we study about the reservoir effect as well as the contribution to reducing of different kinds of shrinkage by biochar. When it comes to the reservoir effect, there are many ways for us to do it. And of course, one of the ways that I hope to try in the near future is to physically see how water is distributed in the mortar mixture in the presence of biochar. But what we published a few years ago is to make use of what we call pre-wetted or pre-soaked biochar and to see how that affects the properties of mortar. So this is, again, not a very, very new idea. And as shown in this picture, when you have a pre-wetted lightweight aggregate, okay, that can help to initiate internal curing. And that has been shown time and again that it is a very effective way of increasing the rates of cement hydration and therefore the compressive strength at early as well as late age. So with that in mind, we explore the influence of pre-soaked biochar on strength and permeability, again under 2 curing conditions. And this is what we found, right? And focusing on what I've highlighted here, and that is the depth of water penetration under an external pressure is much lower when you have pre-soaked biochar for both moist curing and air curing. And the same story can be seen over here when we talk about a comparison of the 28-day strength when we make use of pre-soaked biochar, which is indicated by these 2 bars here, compared to when you make use of dry biochar, which is shown over here, as indicated by my pointer. So the key results here is this, that moisture retention and the resultant enhanced hydration is the main contribution of pre-soaked biochar. And the fact that we have put that, we have tested them under air curing condition, means that there is a clear reservoir effect of water coming out from the pre-soaked biochar in order to sustain the cement hydration in the environment around it. And this has led to the difference between water absorption, water penetration, and compressive strength between mixture containing pre-soak and mixture containing only dry biochar. And that brings us to yet another milestone, in my opinion, starting in 2018. And it is the application of biochar with other additives. One of my, I would say, favorite work is this one by Ekta and Ajit Salma, friend of mine in New Zealand. In 2018, they studied how, by addition of biochar together with recycled concrete aggregate, which, by the way, I'm not sure about the situation in your respective countries. In Singapore, the making use of RCA, or recycled concrete aggregate. In Singapore, we call it RCA rather than RAC. It's getting really very popular. So they show that by adding a biochar, they can control and even enhance certain property of concrete that contains RAC, or as in my case, we call it here RCA. Along the same line, my team also produced a few papers on the use of biochar together with other additives, pozzolanic additives such as silica fume, rice husk ash, and so on. Starting in 2019, biochar mortar received a different types of spectacle, I would say, and it's fortunate that my team and I we have participated in that worldwide effort, and that is looking at how biochar mortar can play its role as a resilient or climate resilient materials under harsh conditions, including high temperature, resistance in high sulfate and chloride environments. And an article of ours is now under review, and hopefully it will be published by end of this year. And of course, making use of biochar as a way to enhance self-healing in concrete. And of course, going forward, I'm beginning to see people pushing the envelope, and it's really good to see that. One example is in the area of advanced characterization of biochar in mortar. And I've just attended the PhD defense by Ekta and Ajit Salma. Very soon, I suppose they'll be publishing an article on how they have made use of nano indentation for biochar mortar, specifically on measuring the strength as well as the modulus at every or at different spots in the mortar itself. So after I've talked about so much and spending about 44 minutes talking about biochar, let us have a summary. After all, this is something for us to learn from one another. So you have seen all the milestones that I've highlighted. Definitely, I've learned from the works by other people. And if I may boldly summarize, this is how I think biochar has helped in the mortar or concrete mixture. Okay, what we see here is an air void in mortar matrix, and the gray part is, of course, a mortar, simplistically. And there are a few key ways, I would say 4 physical ways that we can imagine biochar particles helping. All right. Firstly, if the biochar particles are small enough, you can imagine air voids being formed around it, and because of that, it helps to break the path of any fracture line that may go through or may threaten to go through these air gaps, thus making it a little bit harder or increasing the fracture energy. Also, when you have water around, And of course, if we are talking about dry biochar particles, some of the water will definitely go in. So for those of you who have literally done mixture with biochar in the mortar, you'll find that it can get a little bit tough for you to get the right workability. But that has already been solved by adjusting your water as well as a super plasticizer ratio. So that's no longer a problem actually. But what we found is that if you have biochar that can help to keep some of the water, it helps to densify the neighborhood in the mortar mixture. And not to mention that the additional surface area afforded by the biochar particles can actually enhance the formation, the nucleation of the cement hydration products inside. And of course, as I've alluded to a few times just now, these pores in the biochar particles can also act as temporary water tanks to effect the reservoir effect in order to sustain the hydration in the mortar matrix around it. So what are the opportunities ahead? I would say that this field is a rather new field. It's less than 10 years. And so much has happened in these 10 years, all thanks to the global effort, working very hard with conviction in this area. But personally, I find that there should be more applications or studies on application of biochar concrete under harsh conditions, all right? And even, under extreme weather, extremely cold weather, in order to study the freeze-thaw behavior of a biochar concrete. And I think all these are in line with the so-called larger picture of climate change adaptation. Theoretical modeling. We have gone through almost, I would say, all the papers written on concrete containing biochar. And we find that any theoretical deduction that came out from these efforts are basically based on curve fitting in order to find out at any one time how 2 or even 3 parameters are related to one another. There's absolutely nothing wrong with that, but I feel that the time may be right, given that we have a good 8 years of data out there, to see whether we can have a more fundamental theoretical understanding of how biochar interacts with the cementitious medium. And this model can be both descriptive or predictive in nature. And it might be time for us to really refine our mental model. To me, at least, the mental model that I have as I speak to you about biochar particles in mortar is that it is what I call a strong mini sponge. So it's not just about the size that matters, but the kind of pores and holes that this mini sponge holds that matter. And very quickly, in the past few years, I've started something on a theoretical model, starting from the very fundamental, and it's to find out how pores are actually formed and evolve. I presented this in Italy last year in the biochar conference, and came up with the idea of what I call pore wall bubbling. And that is, we consider non-uniform but localized expansion of the wall of the pores. And so if you can see over here, this is an O pore. And when you apply heat, this wall bubble will be formed and it expand to engulf a neighboring smaller O pore. And of course, there will be newly formed pores and so on. So how do we actually operationalize this using a mathematical model? So my effort for the past 1 year has been to come up with a model like this, which is almost written up already. And I'm going to submit it to a journal, a special issue journal from this conference. And in this case, I have a rather simplistic idea of how this pore expansion can actually happen in a mix of 2 different types of movement, and that is pore protrusion and pore expansion. So this is the mathematical framework, which I don't intend to go through in details over here, but a few things to emphasize, and that is that it contains the kinematics as well as a delta T, which represents the length of time of the pyrolysis or gasification in the production of this carbonaceous material called biochar. So this is the prediction of the pore size distribution at 300 and 500. Okay, what I found is that if I were to apply a certain boundary condition, which I call the large expansion approximation, it works well for 300, but not good enough for 500. And one of the possible reasons may be that when you jack up the temperature of production of biochar, you will tend to have a wider range of sizes, and therefore your large size or large expansion approximation will not work to describe the smaller mesopores or even micropores. So I've come up with an improved model, and I'll be testing this in a few days' time. And opportunities ahead, of course, construction 3D printing. We have begun to experiment biochar and see how the capability of biochar to control water distribution in the mortar mixture can enhance certain aspect of its rheology and even the actual printing outcome. So this slide was taken from my keynote speech at the Australian New Zealand Biochar conference last year. And this is my lab in NUS, the construction 3D printing lab. Many people have put in a lot of time and effort to make this happen. Kudos to all of them. This is the machine that we have donated from China, Nanjing. It is a gantry kind of printer. And allow me to play this for you. Okay, this texture is one of the best that we have achieved with a certain degree of biochar, but it is still not the best because the buildability is still not good enough, given that there's a spread. So we have since improved, and now waiting for the 28-day mark to be reached in order to do further testing. So again, what's so different about this mixture is that it contains a certain percentage of biochar, and we hope to see that biochar, or with the addition of biochar, certain performance parameter and properties will improve. Challenges ahead, and with the next 5 minutes, I would like to quickly go through this. Whenever I present about the progress that we have recorded on biochar mortar, almost always somebody will ask me about the prospect of commercialization. From lab to market is always a very, very tough journey because it's no longer at lab scale, and you have to promise that whatever feedstock that you are going to make biochar from, okay, the feedstock must be available and it must be consistent. Consistent not only in the quality that would contribute directly to the enhancement of physical properties like water absorption, as well as compressive strength. You have to make sure that it's consistent in a way that it does not contain any impurities and potentially hazardous material over the limit set by the local law. This is going to be tough. And also, what's the impact due to decreasing global sand availability? I'm not sure about your respective countries, but in Singapore, okay, this question is always in our mind because for the past 5-10 years, we have already encountered a few episodes in which we have to look for alternative to sand for concreting. So can biochar be the alternative? Well, this question is a tough one because if we can't even address the question of feedstock availability and consistency, then it will be quite difficult to talk about replacing or substituting sand with biochar. And of course, if you are to zoom out and take a look at how we can develop a biochar concrete ecosystem, we have to ask ourselves, what are the policies and management issues that we need to put in place? Can what I would call industrial symbiosis arrangement, in which different companies are to come together to form a network, and every company is to pass either waste or resources to another in order to drive their local processes. Can this arrangement be one that we can use to grow biochar concrete within an ecosystem, or maybe into a future of circular economy? This is something that a friend of mine, Dr. Andre Masek, and I, and of course together with Dr. Sradip Gupta, has just written on. It's going to come out in a book hopefully pretty soon, and that is on what we call biochar-based circular economy. So in conclusion, as I've mentioned just now, biochar, mortar, and concrete is a relatively young field, and I would say that it's very lucky because it really benefits the development for the past 8 years, really benefit from a group of pioneers who really pushed out this new idea in the very beginning. So it has been a very productive 8 years with important milestones that I've shared with you. The combined effort and hard work of several teams across the world. But even that means that there are many new opportunities await us, as I've shared with you. And of course, along the way, there will always be technical challenges. But in this case, I would say that these challenges really transcend science and technology, but into the realms of policy, of management, of economics, and maybe just human behavior. All right. So lastly, I would like to share with you some of the reports about what we have done in NUS. Okay, this appeared in a local newspaper, Straits Times, and a very brief video of what they produced for us.
With concrete could actually make buildings more durable. They also be more environmentally friendly because it puts wood that would otherwise be disposed of to good use. Vanessa Lim with more.
It's an ingredient for a recipe that will make concrete stronger. This tray of sawdust is going to be cooked under heat and converted into a special type of charcoal, which can help to improve the mixing process for concrete. And it's environmentally friendly because no carbon dioxide is produced. Called biochar, the charcoal has many holes on its surface, which means that water can be easily absorbed and retained. While they are smaller than a fingernail, these shavings can help to create concrete structures 20% stronger than those made without it. Beyond making buildings safer, the new concrete mixing method could also help to put wood waste to good use as it recycles sawdust from it. By strengthening the concrete mixture, items could be made thinner and lighter while still retaining its strength, resulting in less concrete being used.
US research.
So nothing is possible or will be possible without the support from our Ministry of Education, and of course the many different fundings coming from the National Research Foundation through either the Intra-Create seed funding or even the NAMIC, which is our National Additive Manufacturing Innovation Cluster. So in case you are interested to see how you can learn more about biochar, and not just biochar concrete, there's a relatively new journal out there right now. And it's just been launched a few years ago, and it's called simply Biochar. So with this, I'd like to thank you very much for your attention. And of course, once again, thank you very much for giving me this opportunity.